All right, everyone, thanks for coming. My name's JF. I work at Apple on Clang, and today I'm going to talk about signed integers being 2's complement. So it's going to be a fun story here. So how did I get started? Well, so I've been on the standards committee for a while, and there's a bunch of stuff that you can do on the standards committee, just too many for one person to tackle. And so I'll just usually pick things that get me enraged or that get my users enraged, and I'll try to tackle them one at a time. So as all good things, this started on Twitter. So a few months ago, I tweeted out this thing where I said, hey, fun fact number one, signed integers can be 2's complement or 1's complement or signed magnitude, and overflow is therefore undefined behavior, right? So the rationale that the standards has is that it's undefined behavior because if you have these three representations, then like you don't really know what's going to happen when you overflow, right? So that was kind of the rationale. And so fun fact number two from Twitter again was that atomic integers guarantee 2's complement behavior, right? So since C++11. And so therefore, they don't have any undefined behavior when you overflow. So this is a quote from the standard here. Remark for signed integer types, arithmetic is defined to use 2's complement representation. Right? So the SG1 crowd, so the concurrency parallelism crowd, was very, very specific about this. Now, what's interesting is this little side note here. It's not always true, right? So the way operator plus plus, for example, is defined on atomic of int is its equivalent to return fetch add of one of the value plus one. Now, you'll notice that there's a little plus here, which is not atomic, and so therefore there is undefined behavior in atomic addition. Now, realistically, it's kind of a fun fact. It doesn't actually do anything because nobody optimizes based on that. Nobody takes advantage around atomics of the fact that that little plus plus is technically undefined behavior. And so what the committee ended up doing is just filing the defect report, and we're trying to get it fixed. But what's interesting is the committee decided around C++11 time to make this change, right? To make atomics have defined behavior. And the way it worked is the concurrency and parallelism group came up with this thinking, well, atomics with undefined behavior are bad, therefore we won't let that happen. And then they gave that to the rest of the committee. The committee said, whoa, whoa, whoa. These people, they do concurrency and parallelism, they must know what they're talking about. And it turns out they were just like, it sounds bad, so we won't let it happen. And so it's kind of it just kind of happened that there's no undefined behavior there. It doesn't really make any sense, right? But at the same time, it doesn't make sense to optimize the atomic additions or whatever. You don't have hot loops with atomics or anything like that. And so that's kind of what got me started. I kind of tweeted that and we made fun on Twitter. That was great. But there's a kind of core of frustration in me, and it's code like this. So I've run into code like this fairly often. It's code that'll try to check if an overflow is going to happen. So say you have user code that comes in and gives you two values, or you have one value and you take the other value from the user. And the user's trying to mess with you, right? It's usually an attacker or something like that. So you're like, I'm going to be clever, and I'm going to check if someone's trying to like do something bad by overflowing, right? And so you do this, right? Now, the problem with doing this is this is the assembly that you get out of it, right? So on the left is x86, on the right is ARM, and it's kind of shaky because it's really bad. It's not actually doing anything, right? Like this code is just wrong, right? The code gen is just wrong, right? It's not actually checking what you want. What it's doing is just a shift right and then like just returning the top bit to see if it was negative or not, right? So it's not checking for overflow. It's not adding anything. We told it to add, it didn't add because signed overflow is undefined. The compiler goes in and says, well, there's no way that could overflow, and so I'll just check whether one was smaller than the other or something, one was negative or something. So one thing to note is this code example that I have here only checks for positive overflow. So it's not checking for negative overflow, right? So in this example, I'm assuming that I know the input is positive. So I'm just looking for the overflow going above int max, right? And we'll get into that a bit later and have more code. So, OK, this is bad. And this is one of the things that personally I'm like, yeah, this is really not good, right? This type of code happens really often, surprisingly often. I've pointed it out in code reviews a handful of times, and it's the source of exploits semi-frequently if you look for it. So this is bad. And you're writing the obvious thing, right? Like you as a human know how integers work when you add them and everything like that. You know that it's a, say, 32-bit integer. And you know that if you try to add the two things together in a 32-bit value, it'll wrap around, right? So you're trying to check if I add them together, is it going to go negative, right? Because you know maybe that's how the hardware works. And I'll dive into that a bit later, right? So the question that I then get when we do code reviews is, okay, well, we can't fix the standard right now to just do what we want here. What code should I write? Well, okay, so there's a few things you could try to do. The kind of generic way that you can do it is something like this, right? So you'll say, okay, well, I have the left-hand side and right-hand side, and I'll just make unsigned t, and I'll add them together as unsigned, and I'll compare to the right-hand side in this case, or the left-hand side. And this is the code it'll generate, right? So you'll get an add and then set b, which sets a flag if the byte is below in x86, or a conditional set on ARM for HS. HS is the carry bit is set, right? And so in both cases, what you're doing is you're turning it in a register. In the case of x86, you're returning it into AL, which is like just the A register. So AX, EAX, and RAX are that register in x86. And on ARM, W0 is the register that you return things in. Right? So it's just the calling convention. Right, so this code is correct. It'll check for positive overflow correctly. And the reason it's correct is because in C++, unsigned overflow is well-defined, but signed overflow is not. Right? So what you're doing is you're literally saying, translate it to an unsigned number, and then do the addition, and then just check whether it's now negative or not. The sum is smaller than the left-hand side or not. And really, this is the code you want to get generated, but this is non-intuitive code. If you gave that code to most people, they're like, this is confusing, right? It's not obvious that you have to write this. So you're like, I don't know, like this isn't great, right? When I do a code review and I tell people just write this thing, it's not great. All right, so there's other things that you could write. So here's another example of what you could write. You can say, well, what I want to see is if you're going to overflow the maximum number, right? So what you say is, I know things are commutative, and what I'm going to do is take the maximum value, the thing I don't want to exceed, remove the right-hand side from here, from it here, and then compare it to the left-hand side. So what you're doing is, instead of saying, I'm going to exercise undefined behavior to see if I would get undefined behavior, right? The first example I had back then. What I'm doing here is I'm saying, were I to do this addition, would it overflow? Right? Does that make sense? Now, the code you get out of this is kind of terrible. It's not as good as the code I had before, right? So you have to synthesize the immediate. On ARM, it's two more instructions. It's still kind of expensive. On x86, the immediate is also kind of expensive. But it's decent code, right? It's effectively doing the same thing. Still doing synthesize the immediate, do a subtraction, compare, and then either do a set or a conditional set, right? And in a lot of hardware, the compare and conditional set are kind of fused together. It's mostly free, right? I'll take questions at the end, please. And so again, just to read the assembly here, set L says set byte if less on the left-hand side, the x86 code, and on the right-hand side, the conditional set for LT is less than, right? And again, this is only checking for positive overflow in this case. So if you had a negative number coming in, well, there's two things to notice. If you had a negative number coming in, you're not actually trying to check if adding the numbers would do a negative overflow, right? So we're just not handling this case here. But also, you would exercise undefined behavior here, right? Max is int max or something like that, and you're subtracting the right-hand side. If the right-hand side is negative, you're going to overflow and you're going to have undefined behavior. Now, it happens that the compiler doesn't take advantage of this fact here, but it is still technically undefined behavior. Doesn't really matter all that much in this case. But it's not great. You know, you read that code. If you ever read that code, you'd be like, what is going on? This is ridiculous, right? All right, so here's another example. We can do more terrible things. So I remember how I mentioned the atomics don't have undefined behavior when you add them? You could do this. So what I'm doing here, this is C code, right? So I'm using atomic int, but std atomic works the same way. And what I'm doing is I'm saying, aha, I'm going to create an atomic on the stack, and I'm going to add the thing to it, and then I'm using the comma operator because I'm a great person, and I'm going to do it. This is exactly the same code as I had on the first slide with code, except using atomics. Now, obviously, this is completely unintuitive, but it'll do the right thing. Now, the problem with that is this. The code looks terrible, right? And what it's actually doing here on x86 is it's using the lock prefix to do the addition, and it's doing move, the compare, and whatever. It's effectively the same thing, but it's terrible code, right? And the reason it's terrible code is because this lock is actually kind of expensive. And the same thing on ARM, except on ARM, you don't have a lock prefix. All you have is a load link store conditional, and so it has to be a loop, right? So this addition is now a loop on ARM. This is terrible, right? But it was a joke. You're just kind of swearing, but like this is, I didn't mean for anyone to write this code. As a compiler author, I think we should be optimizing atomics, but not these ones. Nobody should write this. This is terrible. If my compiler optimized this, it's a waste of my compiler's time, honestly. But it's a bad idea, but it's funny. All right, so here's another thing you could do. Clever people will go in and say, well, actually, bit fields are special, right? Now, the reason bit fields are special is because when the left operand of an assignment operator is a bit field that cannot represent the value of the expression, the resulting value of the bit field is implementation defined, quoting the standard here, as you all know. And so what's funny is you look at the code generation, right? So instead of having undefined behavior, I'm now like, aha, I'm going to have implementation defined behavior, compile it with Clang, boom. Doesn't really work. I get the same code as on the first slide. Why is that? It's implementation defined. Clang said undefined behavior. What's funny here is that GC and MSVC produce the code you would want to get out of this, and so does ICC. And so what's really great when you lean on implementation defined behavior is that you test on GC, does the right thing, good, ship it, recompile to Clang, doesn't work anymore, right? That's terrible. Okay, so let's not do that. Okay, so what else could we do? Well, we could go and do the right thing, right? So I was saying I'm just checking for positive overflow. Here I'm going to check for negative overflow as well, right? So I'm going to say is okay, well, here's the min, here's the max. I'm going to check if it's negative. If it's negative, I'm going to do this thing. If it's positive, I'm going to do the other thing. Okay, this should be fine, no undefined behavior here. The problem with doing the right thing is the code is terrible, right? Like this is really bad code. It's not that terrible, but there's a lot of code. You're doing a check and a branch and whatever else, and synthesizing the immediates, and at the end of the day, that's a lot of code for just checking for overflow, right? So, okay, I did this code review, and people told me, what do I do? And I showed them what they should do, and this is really the only way in just pure C++ to do the right thing, right? And the code you get out of it is terrible. I should file a bug and go fix it. I haven't done so because it's on YouTube now, so someone else is going to do it. But okay, we could actually do something better if we kind of ask the compiler for help. So there's this thing in the compiler called Builtins. You can do Builtin add with overflow. What it does in this case is you put a value of the type you're trying to add on this, you pass it as a reference, and then it will put the result in there, and it will return to you a bool saying whether you got overflow or not. And what's great with that in Builtin is they'll define both positive overflow as well as negative overflow. And the code you get out of it is pretty sweet, right? So what it does here in this case is it uses the CPU's flags to, instead of just checking for like positive overflow, check for both. And it has, in the case of x86, the setO instruction was just set if overflow bit is set, right? So one thing to understand about CPUs is when you do things like addition, multiplication, and other stuff like that, they'll update internal flags. So the carry flag, the overflow flags, and stuff like that, all CPUs have a different set of flags, but they kind of morally do the same thing, right? They just track state about certain things. Because doing addition is just a bunch of wires doing something, and then there's one wire that comes out, and that's the carry flag or something like that, right? So if you look at your compiler manual, or your CPU manual, it will explain which flags you have. Now, luckily, compilers do that for you, and we do a good job at it. That's the type of code you get, right? So this is perfect code for what I'm trying to do. I just want to know if overflow is going to happen, and this setO instruction does exactly that, right? So remember, C++ has undefined behavior when you do signed integer addition. Your hardware does not, right? And so the source of a lot of frustration is I was trying to check for overflow for some security reason or whatever else, and I know for a fact that my hardware can do it really, really cheap, right? And it doesn't do it for me right now when I do it from C++, right? The language is kind of fighting against me, or I'm fighting against the language, whichever side you want to be on. So I declare victory here, but it's not that great. If I wanted to write a library that does all these things really well, I'd have to use all the built-ins. There's a bunch of libraries that you can use on the web that do that, but it's not great, right? You have to know to do this. It's a big gotcha. So that's what got me started into this, right? Just some Twitter fun and then like actually running into bugs. But I'm not the only person who's ever run into this. In fact, there's a bunch of famous integer overflows. I'm going to go through a few of them, not a lot. So one example you'll see a lot when you start using the internet to find them is stuff like Stack Overflow. Right? So you'll look on Stack Overflow, like User Mystical and Zerk MS, and they have questions that are pretty well phrased. They're like, well, I did this thing and something weird happened. Why is that? Why did the compiler do this? And if you look for those questions, there's actually pretty decent answers. They explain to you exactly why a compiler would want to do what it's done. I know the text is small, it's on purpose. I want you to just like look at the slide, look at the Stack Overflow thing later. But the idea here is that the compiler has reasons to try to say like, oh, well, I'm going to assume that your loop trip count can't overflow because of these reasons. I want to do the trip count as the value you're incrementing instead of going from 1 to something or whatever else. Right? So there's actual reasons for why the compiler can do transforms that tend to pay off if overflow doesn't happen. Now, a lot of people think that these reasons aren't really good. We'll dive into that a bit later. But that's like, if you just look around, that's what you'll find on the internet right now. But there's a bunch of other overflows that have happened over time that got kind of famous. One example like that is PacMan. Have you ever played PacMan? I think it's like the most recognizable game ever or something like that. In PacMan, when you play the game, there's a kill screen at level 256. So what happens is when they developed the game, nobody thought you'd ever get to 256. And level 256, if you've ever seen it, has like the right-hand side just kind of garbled. There's an out-of-bound bonus item, basically. So they try to draw the bonus items, and what happens is you just go out of bounds because level 256, if you have an 8-bit thing, just overflows. And so it just goes out of the array and just draws random stuff. Instead of having like cherries and oranges and apples, you get like just random ASCII and other stuff. And then that makes Inky, Blinky, Pinky, and Clyde just really, really sad. That's the name of the ghosts. And the game is playable at that level, but you have to play it from memory. You have to remember what state of the game is to be able to play it. It's kind of silly, but then you're playing PacMan, so nobody really, really cares, right? So you get random ASCII instead of fruit. Okay, you got undefined behavior-ish, right? That was written in assembly, and it wasn't really planned or anything. But you know, it's a nice bug. It's fun. Okay. But there's other bugs that happen over time, right? So have any of you played Donkey Kong? The original Donkey Kong? Yeah? Yeah? Or Jumpman? So Donkey Kong had this thing where as you play the game, there's this bonus counter, right? So the idea is you play the level, and if you finish quick enough, you get more points. The idea is I don't want you to stand there and just jump over the barrels for like 5 hours. I want you to make forward progress because you'll get more points. And if the counter runs out, you're going to die. The game just ends if you lose. If the bonus counter goes to 0. And the way they calculate the bonus counter is they take the level, multiply by 10, add 40, that's the bonus counter, right? And at some point, they just clamp the bonus that you get. So at some level, at level 6 or 7 or whatever, it clamps at some big number. And that's the bonus you get for the rest of the game, right? Now, the problem is when you get to level 22, if you do the math here, you get 260 base modifier. And the problem with that is it's an 8-bit counter, it overflows, goes back to 4, and now you have just a few seconds, like 2 or 3 seconds to play the game, and you instantly die. So that level isn't actually playable because the bonus counter goes to 0 way too quick for you to do anything. So you run out of time, you die. So that's another kind of kill screen in Donkey Kong, fairly early game. Kind of interesting. There's other interesting games. So anyone played Civilization? Right, fans of Civilization here. So Civilization has this amazing bug in the original version. So the game, the idea of the game is you build up a civilization, you play as a world leader or something like that, and there's other world leaders playing against you. So the artificial intelligence tries to attack you or something else, and one of the world leaders is Gandhi. Now Gandhi is really nice, everyone agrees. Right? So the way the game is programmed, his base aggression is 1, whereas everyone else has other base aggressions that are bigger. Gandhi's really nice. Now the game is really well crafted in that as you discover things, there's things that change, like you can take boats and go other places and whatever, and one of the things you can do is research different forms of governance. And so once your character discovers democracy, that character gets an aggression modifier of -2. Now at this point in the talk, you should all figure out what's going to happen, right? Gandhi is really nice. He discovers democracy. What happens? You get a negative overflow. He gets real aggressive, right? And the way that manifests, which is like hilarious, is he starts nuking everyone. Now, what's really great about this bug is Sid Meier decided that this is kind of an Easter egg now, and every game since then has been bug compatible with the first one, whereby Gandhi is really trigger happy when he gets nukes, right? So it's funny, right? But it's weird. It wasn't intended, but it's funny. So there's another game called Chrono Trigger. There's this boss called Dream Devour, and when you have big bosses, what do? You give him a lot of health points, right? So 32,000 health points, really hard boss to fight. But you're clever as the player. You've played video games before, played PacMan, played Donkey Kong, played Civ. You're like, that guy, not that hard to beat. I'm going to heal him. If you heal the boss just enough, you're going to overflow the 16-bit counter. What happens when you do that? He dies. That's great. It's really funny, right? You just kill the boss by just healing him. That's great. It was supposed to be hard. It was really easy. So really, you're just killing the boss with kindness. It's beautiful. OK, so next thing that's really funny, Bitcoin. So thank you. Early on, Bitcoin had this thing in 2010. There was just one reference implementation. And at some point, people in the forums looked at stuff, and they're like, oh, what is that? There's these 2 transactions for 92 billion Bitcoins. There's not that many Bitcoins outstanding. What happened? And so the quantum, or whatever you call it for Bitcoin, is 10 to the 8. You do the math. 2 to the 63 divided by 10 to the 8. That looks bad. What is that? Well, it turns out that the reference implementation didn't check the 2 transactions when put together, didn't cancel each other out and wrap around. And so the blockchain, for a short amount of time, contained ginormous transactions which weren't supposed to exist, right? Now, what they did is they forked the blockchain as one does, and that fixed the bug. That was number 5 of 37 common vulnerabilities in Bitcoin. It's kind of funny because it's Bitcoin. But it's a bug, right? It's another overflow bug. Still kind of funny. Now, a bit less funny, airplanes. Recently, in the last 10 years, there's this airplane that came out that I won't name, and they had this problem. They reported to the FAA. They looked at their code well after the plane was in production and whatever, and flying. You've probably all flown on one of those, actually. And they realized, oh shit, if we wait long enough, the generator control units, all 6 of them or something like that, are going to have an overflow bug after 248 days. And so that sounds really bad. And do you know what the fix is for that? So instead of having them overflow and potentially do something, I don't know what a generator control unit does, but I don't want it dying out in the plane while I'm flying. The fix for that is in the checklist before launching the plane or whatever, you just reboot the plane every 8 months. It's kind of funny because rebooting a plane is a thing now, but it's not great, right? Like airplanes are meant to be kind of stable, and they're really good at being that way, but that scares me a bit. Now here's something a bit less funny. There's this rocket called the Ariane 5 that exploded on first launch. The problem it had, and it's not really an integer overflow bug, so they had this 64-bit floating point number that was that was converted to a 16-bit integer, and they had tested stuff quite a bit, but once they actually launched the rocket, the 64-bit floating point number representing velocity was just way too big, and it overflowed when converted to a 16-bit sign integer. Now, anyone want to guess what happened when they did that?
The computer giving information, so it decided it was all
right.
Destructed itself?
Kinda, not quite. So it just exploded. But what's sad about this, and what I read on the internet, so it must be true, is that code didn't actually need to be running. It was for a previous version of the rocket, and so it did a thing where it ended up crashing, and then crashing the whole thing. But that changes what a software crash is to me, right? That's not really fun, right? I have way fewer laughs at this than at Bitcoin. So it's not that funny. And so I've given you examples of famous integer overflows. Okay, I think a lot of you probably like integer overflows for some reason. A lot of you probably don't. But inevitably, as compiler people, when we start talking about integer overflows, what we run into is the angry programmer, right? And I was going to have a joke here about how Linus is the patron saint of angry programmers, except he's promised last week to reform, and so I want to see if that'll happen. I didn't change my slides, so I'm still going to quote him. Because he doesn't swear in these quotes. So he's angry, but he's sometimes right. So here's a quote from Linus. This is why we use -f_v and no strict aliasing, etc. The standard simply is not important when it is in direct conflict with reality and reliable code generation. Now, I'm going to extrapolate a bit here and say that what he means when he says reality is my hardware does this when I add, right? The instructions I showed you earlier, when you add, it just wraps around. In fact, your hardware does not know whether an integer is signed or unsigned. It only has an add instruction, right? So adding signed and unsigned integers is exactly the same thing. And so why he's frustrated is he knows assembly, I'm assuming, and he says, well, like, the instruction should be this. I asked you to do this. Why didn't you do this, right? And it is frustrating. Let's not talk about strict aliasing in this talk, right? But he's frustrated, and this type of frustration I've seen online quite a bit. So here's another quote from our buddy Linus. Have you ever seen code that cares about signed integer overflow? Yeah, getting it right can make the compiler generate an extra ALU instruction, so arithmetic unit instruction, but once in a blue moon, but trust me, you will never notice. You will notice when you suddenly have a crash or security issue due to bad code generation. So I agree with him that you'll notice when you have a security issue or bad code generation. You can see how the code I had on my first slide that was trying to check for overflow by exercising overflow would be a security issue, right? Now, at the same time, if you look at the examples I just showed you, I want you to think about how many of the Donkey Kong, whatever else, would have been fixed by having wrap on overflow or trap on overflow. We'll get back to that in a minute. So, Linus says use frapv, ftrapv, or ubsan. It's another thing you can use, undefined behavior sanitizer. All right, let's use those. We're good. Right? Linus said do it. Let's just do it. Look at the code that you get out of it. This is the code from the first slide. It does the right thing, right? It does the add and the compare and the set to check if I have positive overflow when I do frapv. And if I do ftrapv or I set ubsan to trap on undefined behavior, I get code that does the comparison and then branches to a trap if it happens. Right? So there's many ways to configure ubsan. That's one of them. It'll just trap. Right? So ud2 is a trap on x86, and breakpoint 1 is, well, breakpoint is a trap on ARM, and you can set an immediate. So OK, that does what I want. Linus said to do it. Declare victory. Now, there's a problem. If you go back and think about the examples I gave you of overflow on PacMan, of overflow on Donkey Kong, and whatever else, how many of those would have been fixed by wrapping behavior? 0. How many of them would have been fixed by trapping behavior? 0. OK, so the rocket would still have exploded. Bitcoin would still be a bad way to invest anything. Like Donkey Kong would still be kind of a fun game, but I still couldn't get past level 22, and so on, right? So Linus has somewhat of a point, right? And when you're doing security checks, he's correct that you wouldn't have a security bug because the compiler did a thing you didn't ask for. But all the other famous examples I showed you would still have these bugs, right? Except for the Stack Overflow example, the very first one, right? Like those loops would behave as the programmer expected instead. All right, so do we declare victory? Not really. So let's stop the fireworks and go back and say, well, I'm on the standards committee. Why would I change anything? What could I change? Well, so what I did is I decided, well, no modern hardware targets C++ without being 2's complement. I'm going to have to prove that, but that's my premise. And then I'm going to say, well, really this sign overflow thing or this representation thing is really a burden on the language. You could do away with it. And then remove the number of gotchas that we have. It'll be easier to understand the language. But really, it's not clear that changing the arithmetic makes sense, right? So changing the arithmetic to do wrapping or trapping or whatever might not be the right thing. But I'm going to write a paper where it does, right? So the original paper I wrote proposed that we make signed overflow wrap. And I'll get into that a bit later, right? And a thing to remember is when I'm talking about overflow, I'm not just talking about addition, subtraction, and multiplication. You can also get overflow when you get the absolute value of something, right? So absolute value of int min has undefined behavior, and at least on a 2's complement machine. And then int min divided by -1 also has undefined behavior, right? Because you don't have a way to represent those, right? So it's not just like, oh, add is a thing that's weird. It's really all these other operations that are weird. So I took this idea, and I wrote a paper with this premise. There is one true representation for signed integer, and that representation is 2's complement. OK. Is it controversial or not? Kinda, right? So I posted that to internets. It went on Reddit at some point, and Reddit did whatever Reddit does. And not everyone was very happy with me, right? But that was my premise. We'll try to define the wrapping behavior in the first version. All right, so I've been talking about integer representations for 30 minutes now. What does that even mean? Let's step back a bit and look at what that means. So first, in C++, I'm going to think about assuming a pure binary system, a pure binary number system. What does that mean? Well, it means not any numeral system, right? We're not doing Roman numbers or whatever else. We're not doing acoustic delay lines. We're not doing Mercury delay lines. If you open the history books, it's useless, just close them back. It's interesting, but it's not something we're doing right now in C++. And I've been told also that assuming a pure binary number system is arrogant because it prevents the design of memristors with non-binary arithmetic. I don't know what that means, but I've been told that. I've also been asked, does this mean that base 3 computers can't run C++20 code without emulating base 2 for signed integer types? Yes, it does. And then the most frequent thing I hear is, well, there's a bunch of Unisys programmers that are going to be sad without this. And my answer to that is, they're already sad. OK, so why do we restrict ourselves to a pure binary number system? That's my premise to start with. Well, the way I restrict myself is because the C++ standard already does so. Right? If you read the standard today, this is it. It says it's a pure binary number system, and it goes and quotes the, what is it? The American National Dictionary for Information Processing Systems. It sounds really nice, right? So this is what C++ says about signed integers, that they have to fit within a pure binary number system. Okay, step back a bit. C derives from C, right? Now C has this really interesting thing. Extraordinary values. So let's look and figure out where you can find those extraordinary values. So C standard is more restrictive than C++, which is weird when C++ derives from C. I don't know what that means, but C says there's 3 ways to represent signed integers. You can do sign in magnitude, you can do 2's complement, or 1's complement. All right, so it's more restrictive than a pure binary number system. What's interesting is C allows you to have multiple zeros for signed integers. It also allows you to have extraordinary values. What is an extraordinary value? The most the smallest value you could represent, you can decide whether it's int min or whether int min is the next one next to it, right? So whether it's like -0 or something like that, you can make that a trap representation. I don't know of anyone who's ever done this, but C allows you to do it, and that's extraordinary in my book. All right, so C does this. C++ does something more broad. But what does it actually mean? Well, we're going to go to Dant Knuth, obviously. He's going to come in and tell us, well, this is what it means. 2's complement, apostrophe S, means one thing. 1's complement, S apostrophe, means something else. And there is actually a 2S apostrophes complement. And at that point, I close the art of computer programming, and I go back to other things, because I don't understand what he's saying. It sounds really good, though. OK, so then I went back and looked, because computers weren't the first thing that talked about binary arithmetic. And I tried to find what defined binary arithmetic for like our modern society, right? Like the modern Western society learned about binary arithmetic from this cool guy called Leibniz. And it turns out my native language is French. The guy wrote in French. Some of his papers are in French. It's great. He has a paper here. This is the title about binary arithmetic. It's 4 pages. It's from 1703, and it's surprisingly accessible. Like it's just kind of old French, but it's really readable if you know French. I recommend reading it. It's fun. And so what he found out is he had invented binary arithmetic as he had invented many other things. It turns out he was not the only one who had invented that thing. So he wrote a paper about it because he talked to a priest, and the priest told him, hey, I have this thing in China. It's really weird. I don't understand what it is. He showed it to him, and he was like, this is binary arithmetic. Right? So it turns out that people in Egypt, China, India had invented binary arithmetic 1, 2, 3,000 years before Leibniz. Right? So at least like they didn't quite pull a Newton on him, but like they had invented the same thing quite a bit before he had. Now what's interesting is Leibniz took this invention out of nothing, right? The fact that many people had invented the same thing, he took that as a proof that God existed. So binary arithmetic, God exists. Thank you. Or at least according to Leibniz. So that's where, like in Western society, the binary arithmetic definition came from. If you look at it, he has a table that really describes it really well. But recently, when computers came along, people tried out different things. this is what different computers did over the recent history, right? So up to the 70s, before actual modern architectures existed, people used ones complement, twos complement, and sign magnitude. So this other guy on the C++ community, Tom Rogers, did a survey for me of different architectures and what they'd done and different DSPs. And so this is what we found over that survey. There's really only one platform that ever really tried sign magnitude, the IBM 700 and 7000 series. And what's interesting is they had sign magnitude arithmetic except for the index register, which was two's complement. I don't know how you programmed that. But then there was a bunch of attempts, right? And originally, von Neumann suggested doing two's complement. But then after a bit of time, there was like a spur where people were like, one's complement might be a thing, let's try it out. Then they backed off and they stopped doing it. And after the 70s, so late 70s, early 80s, there's all the other architectures that come in, like x86 and ARM and Power and things like that. And they're all two's complement, right? So realistically, if we're going to make C++ and C do two's complement, we got to look at if these hardwares still exist and if they're relevant, right? If the ones that don't do two's complement are used. So let's look at that. So there's recent DSPs, and let's see if they're relevant. Well, there's the Shark family that does C++11, two's complement. There's the Freescale C++03, two's complement. TI, C++14, two's complement. Cirrus Logic, it has a C compiler, it's probably two's complement, it's hard to tell from their documentation. CML microcircuits, it's a fixed ASIC for radio processing, it doesn't seem to support C++, don't give a shit. Synaptic does audio subsystem for voice assistance, and it has some far-field signal processing algorithms, and it has programmable functions and whatever else, but it runs on ARM stuff and other things, it's probably two's complement. Okay, so what does it actually mean when I say two's complement? Well, there's really two things I want to take out of this. First, beautiful animations, but it's really storage versus arithmetic. What I mean by that is when you two's complement, you're doing addition, multiplication, subtraction, and you're trying to increment or something like that, but at some point you got to store it. And I want to disassociate those two things. The storage of two's complement is one thing, right? What you get, where the bits are in memory, and the arithmetic is a separate thing. What I mean by that is if you look at a table of the binary values, this is what it means in one's complement, two's complement, and sign magnitude. Here I'm assuming that I'm ignoring endianness and I'm ignoring bit width, right? So I just have an 8-bit number. And if you look at the binary, you interpret it in one, twos, or sign magnitude, this is what they mean, right? So this is the storage of two's complement, but the arithmetic is really like what happens when you overflow, right? Either positive or negative overflow, or when you do the absolute value, or when you divide, right? So I want to disassociate arithmetic and storage. I think storage is a thing we can define fairly easily in the language. Arithmetic is the thing that might be a bit more contended, right? So I want to keep those two things separate. We're talking about two's complement, but there's two things that we have to tackle at the same time. And specifically, I got very early pushback from the committee because they didn't want to define overflow. And the reason they didn't want to define overflow are actually pretty good. So the rationale I have is, well, I know what the CPU does, right? Like when I do an add, it wraps, and things like that. But there was a separate argument that I've made in this talk so far, showing you previous example of famous overflow, that roughly 90% of overflows are actually bugs. And wrapping wouldn't actually fix anything, neither would trapping, right? So we can argue whether 90% of overflows are bugs or not, whether it's 50% or even 20%. But if C++ comes in and defines the arithmetic of signed overflow and says it wraps, it's probably not fixing anything, right? So none of those games would work any better if we had done the wrapping behavior. In fact, a lot of them were written in assembly and they had wrapping behavior, yet it still had the bug, right? So why not define the overflow? Well, it prevents optimizations, and I'll go into that a bit more later, right? That's one of the big arguments. You do the wrapping behavior, and that prevents me from optimizing things. Second thing it does is it prevents bug finding. And that's a bit of a weird argument, but if you think about it, UBSAN is a valid implementation of C++. But what it does when you do undefined behavior is it tries to trap. It doesn't do it for all undefined behavior, but that's what it tries to do. And the argument here, which I don't really agree with, is if I were to define overflow to trap, to wrap, and then UBSAN is not allowed to do that. It's not a valid implementation. Now, The reason I don't agree is UBSAN has a mode where you can say unsigned overflow traps. That's not a valid implementation of C++, but it can do it. It just means that more code could come to rely on overflow behavior, and so UBSAN would have more false positives. Right? That's really the trade-off we're trying to talk about here. And then finally, the argument that really convinced me is it doesn't really fix all bugs. It doesn't fix most bugs. It'll fix the one bug that I care about, which is the security check, but it doesn't fix anything else. Right? So when we say that signed overflow it prevents optimizations, this is what we mean. Someone did a survey of how GCC used signed overflow to optimize things, and it's really interesting. It prevents some optimizations that are really key to getting good performance, right? And if you go read the blog post, it really explains in detail what each of those transform means, right? But this is at the time all the things that GCC relied on to say, well, if signed overflow is undefined, I can do these things, right? Now, individually, they don't really seem like much, but there's a cost associated to not allowing those optimizations. So I'm not silly enough to go and do measurements and say them on stage. Other people did that for me. Their measurements was that it's roughly 12% cost in a range of 0 to 40%. Right? So some apps got 0% slower, some got 40% slower, and geo-mean average, it was 12%. And the size overhead they observed was about 1%. So size overhead is actually pretty good to do all the checks and whatever, but the perf overhead is quite significant. If you go look at the paper, it explains in details what they did. So it took spec in 2006, the C and C++ subset, and they did a bunch of stuff. And since then, there's optimizations that have gone into compilers so that the cost is probably lower, but I totally believe that it's not zero, right? Even if it's 5%, you don't understand what 5% is to compiler engineers. Like, it's a huge gain. Like, I can spend a year on stuff and not get 5% on like all my applications, right? This is a geo-mean of scientific compute stuff, and it's 12%. This is huge. I can't make it up as a compiler engineer in a lot of cases, right? There's other people who did surveys, like Dan Liu quoted like 28% for bzip compression and 9% for decompression. If you just look online, there's people who did some amount of surveys of like what does defining overflow do, right? So, and then the final argument is that it doesn't fix all bugs. So what does that actually mean? Well, in the committee, Lawrence Crowd drew this little chart here, and he said, well, there's really two types of arithmetic. There's normal arithmetic and there's modular arithmetic. And there's really two types of numbers. There's cardinal and integral numbers, and right now C++ has two of those slots filled out with two different things. We don't fill out the other slots with anything, and you might want to do something here. What I was proposing was making signed integers behave like cardinal numbers and have behave like integer numbers but have modular arithmetic, right? But the argument made was we really want to put more things in that matrix. We want to give you numbers that do different things depending on what you're trying to do. So for example, if you look at the code base for basically any modern browser, they all have what's called like a checked integer or something like that. And they fill that box differently by making an integer that'll properly detect overflow and either return a Boolean or trap or something like that, right? So everyone ends up filling that box differently. And the argument is the standard shouldn't change the language because we have these performance gains that we get out of assuming undefined behavior. We should instead give you a type that acts like an integer, but that allows you to say, if I overflow, trap, or if I overflow, return a flag or something like that. So the argument is we could do a better job by letting the user tell us we want this integer to behave this way here and keeping the performance gains otherwise, right? And they're really, we didn't deserve those performance gains, but we have them right now. If we change the language and we take away those perf gains, it'll make more people mad than it'll make people happy, right? Your battery life is going to go shorter and a bunch of other stuff. It's not great, right? So we don't really want to do this change. So that was the argument the committee had, and I kind of agree. And so what I did is I changed the paper I had to say, we'll define the storage of signed integers, but we won't define the arithmetic right now because this whole discussion kind of said, like, we really need to define integers that'll do the job that people want them to do. They'll say, I want an integer that does this, and they'll have the thing from the standard that does the behavior they want. Okay. And the other thing that I hear from people pretty often is, well, you're all smart people on the committee. Why don't you just do something else? Like, you could change integers to just do the right thing. Now, the problem with that is I have an analogy. You know how C++ has a lot of features, and everyone agrees you got to stay to a subset, right? In my code base, we stay to the same subset of C++. Everyone agrees to that, right? The problem is nobody agrees on what the same subset is, right? And it's the same thing with signed integer overflow. Nobody in the language design world agrees what a sane subset is, for what a sane behavior is for signed overflow. I'm going to give you examples. Right now, what C++ does when you have undefined behavior for signed overflow is just undefined behavior, and otherwise you got to lean on coding standards or checkers to do the right thing, right? So it's a social engineering solution to a problem. A bunch of other code bases, like I mentioned, have these safe integer classes that'll do what that code base wants to do, right? And then you have built-in add with overflow that the compiler gives you that allows you to just do what you think is right. But if you look at other languages, well, Swift, by default, will trap when you have signed overflow, and it has these extra operators, so the ampersand, plus, minus, and multiply operators, that do wrapping behavior instead. So what's neat is the types just behave like normal, they just trap, but if you know that wrapping is fine here, you express it semantically in Swift. That's kind of neat. C++ could do that. We could standardize those operators. All right. Why don't we do that? Well, it turns out that other languages do different things. Rust will trap and debug and wrap in optimized builds, and it'll have library support for integers that behave differently. It's a bit weird, but you know, Rust does some good stuff. Maybe that's a good idea. All right. Well, C# will wrap by default, except in check blocks, where it'll throw a system overflow exception. Okay, that's another design point. Maybe we could do that. But like throwing exceptions on addition is really not a thing that I want in C++. I want fewer throws, not more. So I'm not a fan. Java, it wraps. Okay, maybe we could do that. JavaScript only has 64-bit floating point numbers, so it doesn't have that problem. If you add too much, it'll just lose precision, and at some point, 1 will not be significant enough to affect the number you're adding to. JavaScript also will support big int fairly soon. So that takes us to Python, Smalltalk, and Scheme, which all use big int, big number, large integer, something like that. It's the same solution, but I don't want my addition to allocate, right? If addition's going to allocate, I kind of want to opt into that. I don't want that to be the default. Makes sense for Python, doesn't really make sense for C++. Ada raises a constraint error. I don't know what that means, but that's what it does, right? It's the same as an exception, I guess. MATLAB saturates instead. Okay, so if you try to go too far, it'll just stay there. It's kind of weird, but MATLAB's kind of weird anyways. And my favorite idea is the thing we could do for C++. We can introduce a thing that I called unrefined behavior. So instead of being undefined or implementation defined, it's just something, it's just not that great. I don't know what it actually means, but I like the word, right? I like the idea of unrefined behavior. All right, so this was the background research for everything, right? So I did this background research, tweeted, looked at a bunch of stuff, and looked at what that meant, went back in history, that was cool. Okay, so after you do all this background research for writing a committee paper, what do? You run to the committee, right? Now, when you run to the committee, there's always one problem with this, especially in my case. The one problem I had was this one. So committee has a lot of really smart people that have a varied history, cool backgrounds. And what we end up doing pretty often is we'll play the one-up cool story game, right? So I'll say something, someone will come to me and say, well, actually, right? And they have a like cool story about something. And I'm like, well, this is pretty cool. Okay, and then someone else will come and say, well, actually, and they'll have another cool story about something else. And then after an hour, we realize we haven't done anything. We'll move on to another subject and fix something else, not signed overflow, right? So I had this problem where I knew I was going to get a bunch of stories about how people had used like delay lines and other stuff, and how like Neil Stephenson has a book about Mercury addition and other shit, and like it's cool, but it's not relevant, right? Like I'm on this stage telling you this, but like it's not relevant to the committee, right? I want to spend people's time productively. So what I did is I kind of went in and I said, okay, there's this thing I'm going to do, and I have this cool story rule, right? And someone formalized it for me. So I'm going to put it on the screen right now. But the cool story rule is basically someone's going to show that they have a cool story, and then we're going to think, is that relevant to what we're trying to do? If it's not relevant, we're going to say cool story, and we're going to move on. And if it is relevant, we're going to think about it and actually dive into it. And only, there's a little dotted line that will only cross in social circumstances, we'll do more cool stories, right? So something like CppCon, cool story galore. Standards committee, no. So this person created this website, coolstory.wtf. I recommend you use it in your daily life. If you participate in standards, it's really good. It just has this image here. And it happens to be the guy who created Rust that made this website, so it's great. It's extra great. OK, so went in with a cool story rule, talked to the numerics group, talked to the undefined behavior group, talked to the evolution, the language evolution group. What did they think, right? What was the reception? Well, initially, they really hated that I defined integers to wrap, right? And the title of the paper was basically that, like, you know, the signed integers are 2's complement, right? So it was kind of clickbait already. I was trying to kind of like come in and have people care about this. And so the reception initially was like, we don't want the wrapping behavior, don't define the arithmetic. Once I removed that, right, get rid of the duck, what happened is they just loved it. It was actually kind of great. Like, these three groups saw it, and they kind of calmed down because I removed the stuff they didn't like. And they're just like, yeah, it sounds pretty good. Do these tweaks. Could you do this other thing too? Could you fix like the way like shifting works and other things? Because they didn't like Howard's change. I'm sorry, Howard. But they were like, change other stuff. And one of the things that really made it kind of waltz in and succeed was Tom Rogers' hardware survey, where he looked at different DSPs and other stuff and tried to figure out like, what do people actually use? Okay, so what's in right now? It's waiting on the next meeting in San Diego. So I'll go to the core group. The core group has told me this week that they're really not happy about how I've defined things because they're defined in terms of human, understandable engineering terms, not math. So they want me to redefine in terms of math. If you want to help me with that, that'd be cool, because math is not the thing I can write really well, like in standard E's. But the rest of the committee loved it. Core is going to make the wording really good. And I don't want to make promises, but I expect that it'll be in 20. We have quite a bit of time to make it there. So we're going to define a storage type of signed integers to be 2's complement. And then we're not going to define the overflow behavior. But the committee seems really intent now on defining these other integer types. There was interest before. It's not that I created that interest. I just kind of lit a little fire under that. So that's kind of fun. And if you have proposals, you can bring them to the committee too to try to help with that. Now, what's really amazing with that is at some point, the committee told me, well, C does something completely different from what C++ does. How about you go and talk to the C committee? And I've never been to the C committee. I'm probably never going to go. But someone volunteered, if you write a paper, I'll present it for you. So Aaron did that. That's pretty cool. The C committee loved it too, right? So that's surprising because the C committee doesn't really change anything. They really care about old architectures and other stuff, but they loved it. That was amazing, right? My mind was blown. They want me to write 1,000 little papers to do that change. I'm not sure how to do that, but they want also to adopt signed integers as 2's complement. Now C is going to ship C17 soon, and so that's probably going to be in the next version of C, which is like 23 or 26, or I don't know. I don't know what the shipping schedule is. So what's actually changing? Well, I'm going to commit a sin of presentation and show you a wall of text because I really want you to go and read the paper. There's a link right there about the paper. So there's a bunch of stuff that's not changing. What I've put on the left is the status quo. It's the stuff that if you were to define the behavior of arithmetic, you would have to go and change. I don't think that's going to happen. I think we're going to have library types instead. But the thing on the right is everything that's changing. There's a lot of stuff, but a lot of it is like kind of token little things. But I think it simplifies the language a lot. And I like simplifying the language. So what's next? Well, what we're going to do is we're going to narrow the number of representations allowed both in C and C++. That's the changes I just showed you, right? We're going to tune it a bit, make it more mathy and whatever, but I think it's going to happen. Then we're going to standardize better integer types. That's probably not going to make it C++ 20, but you know, it's libraries. You can use them anywhere. I think it'll be pretty good. But in my opinion, like there's this collection of changes that this makes that simplify the language quite a bit, but I think it doesn't simplify it quite enough, right? I think there's a lot of burden in using C++ for architectures that don't exist, right? The language says, oh, you could have like this architecture that has like 9-bit bytes and other stuff, and I think we could simplify all these things. So here's a list of things we could go and simplify. Some of them are funny, some of them are actually things I want to work on. So I think we could go and just simplify the language a lot more so that like there's fewer surprising things. There's fewer things that come out of writing C++ and it's undefined for reasons that don't actually matter in the real world. Or things that like carbit is not 8. I think that's a bit silly. I know there's architectures that still have it. I'm not sure that they're relevant. I want to do the background research to see whether they are. and say, well, okay, maybe its car bit is 8 or 16, right? Instead, it could be 9 or 24 or random numbers, right? Endian Lil, we all know that like Lil Endian 1, there's still big endian architectures. I'm not sure how relevant they are. We could at least say it's either Lil Endian or big endian, right? That's kind of a nice thing that we could do. We could also say that car is signed car. It's kind of a weird gotcha that doesn't make any sense these days. We could say the pointer is always 8 bytes, right? Because we know they are. Right, thank you for laughing. We could say IEEE 754, right? That's the thing that like people come to rely on a lot more. There's architectures fairly recent, like ARM v7 that doesn't do that for SIMD, but like I think we could look at progressively looking at that, putting it on the list, and maybe in 10 years we can do it or something like that. Then we could deprecate volatile. I think we all agree with that. And then we could also agree, like, sorry Americans, but like dates are written this way, 2018, 0927. That's the only valid way to write a date, right? I don't know if C++ can legislate on that. We'll see. So I've got like 2 minutes, 3 minutes left, 4 minutes left. This was the talk. Thank you. If you have any questions, please go to the microphone.
More of a comment. It seems like you can get
No, questions only.
You can get almost all of these things by just using the int 8t, int 16t, int 32t, right? Because they are all defined to use 2's complement.
Those are only guaranteed to exist if the machine can deliver them.
Sure. Yeah.
Right. So you could use it, assuming your machine does it, which it does, but it's kind of silly.
Right. You can assume it to the same extent that you can assume the pointer is 8 bytes. But
right,
yeah,
right. As we all know.
Totally agree with you. It's great. Thanks.
Cool.
So if there's UB for signed integer overflow and it gives us like 14% more performance, if we made unsigned integers undefined with overflow, we would get another.
Right. So if you design the language from scratch, you would make signed and unsigned behave the same way. I think we all agree to that, right? Like we should. The problem is we can't go back and make things that were well-defined that people rely on, make them undefined. Right? And in reality, there's code today, like a lot of crypto or encoding code that relies on that wrapping behavior just because it's inherent to the algorithm that unsigned numbers do wrapping for their specific purpose. In most cases, if it's a loop trip count or whatever, it's probably a bug when you have overflow if you use unsigned, right? Same thing as with signed. But there's enough code out there that would be a pretty big break and change that we can't just go and fix for everyone. Right? So I agree, if you design from scratch, you'd make them do the same thing, either both BUB or both do wrapping or something like that. But it's like 30 years too late to do that change. But I'd like to see what the gain is, though.
Hey, great talk, thank you. So you had this one slide where you were illustrating or summarizing all the changes in the paper. Can you maybe mention the 1 or 2 things that affect practical everyday programming most?
Right, that's kind of difficult because there's a lot. So if you read the paper, the link I had on there, those same bullet points are ordered in the order of places in the standard it changes, and then you can go and read that. It changes stuff like, bool is now guaranteed to be either be 0 or 1. There's no padding bits on bool. There's no padding bits on certain other things. Like it's just a lot of small things, right? It's not world changing. It's just reduces the mental burden for a lot of things. And I think it kind of unlocks other changes later that then make it easier to say, all right, well, int is either this or that. It's not like just a random number generator, the number of bits that an int has, right? And I think it's silly to have padding bits for an int. It'll still be allowed after my paper, but I hope to get rid of that eventually.
All right, thank you.
So it's very interesting because I kind of remember when I missed assembly. It's most moment was like carry flag stuff, but then carry overflow flag stuff. But then the other one was, and I remember all the days when I multiply something, the results not go into accumulator, but it goes to dx and ax, right? So multiply two, a 16-bit or 16-bit or 32-bit. I don't know that. I haven't done 32-bit assembly, so don't much, but I know I multiply two 16-bit registers. The results go into dx and ax or something, I remember.
Right, there's
And
instructions that overflow
right,
to a
and then
larger
I
number.
can divide that.
Yeah.
So the CPU is designed so that automatically generate bigger number, and then I divide that and go back to smaller.
Right, well, the
number.
instruction does that for you, right? Some instruction
Right,
like
right,
C6 will start smaller with small inputs and generalize, but most CPUs don't do that. I don't think it's relevant here because it's a cool story.
C does not represent, C does not allow me to do that, right? Is there any?
I'm not sure what you have in mind exactly, but we can talk about it later.
Okay, sure. Another comment is
we're out of
that-
time, so I'm just going to cut you off.
Sorry. Okay.
Yeah, we can talk about it later. Thanks. All right, thank you.